Using lazy, greedy, best first search with subgoaling relaxation in numeric planning problems, and the talk is gonna given by Luigi Bonassi.
Okay, hi everyone, I'm Luigi Bonassi. I'm a postdoctoral researcher at Oxford Robotics Institute, and this is joint work with my colleague Enrico Scala. So, in this paper, we focus on numeric planning problems. So, numeric planning is like classical planning, but with also numeric state variables. And this is essentially a very powerful formalism that allows you to model many real-world problems, such as in robotics or traffic control. And in general, undecidable in the sense that it is undecidable, but the can be recovered. I'm going to use that one. Okay, but decidability can be recovered by enforcing bounds on the domain of numeric variables. So, the goal of this paper is to improve forward heuristic search in numeric planning problems. And we do so by strengthening the synergy between best first search and a heuristic that work on a relaxation of the problem. So, intuitively, as I said, numeric planning is as classical planning, but with numeric state variables. You can use these variables to specify numeric expressions and numeric constraints by combining the expression with the usual mathematical relational operators. And you can also predicate on how the variables change their value. Okay, so you can use these two things to define actions in terms of preconditions and effects. And you can also specify a global constraint that represents the goal to be achieved. So, for instance, you can model the flight of a plane by defining an action that has as a precondition a constraint on how the fuel level has to be before executing the action. So, in this case, you may want that, for instance, the fuel level is greater than the distance, and for the effects you have you essentially specify how the fuel changes after executing the action. So in this case, the fuel decreases. So this is a more concrete example. This is a very well-known domain in the context of numeric planning. It is called the sailing domain. You essentially have a boat that can move across different directions, and so you would have one action for each direction that changes the position of the boat on the XY coordinates, and the goal is usually to reach a certain area of the two-dimensional plane to save a person. Okay, and the goal can be easily specified by using by defining a linear constraint. So more formally, a numeric planning problem can be formalized as a tuple. You have the Boolean and the numeric state variables. You have the constraints, which are formulas over numeric conditions and Boolean conditions. Actions are specified, as I said, in terms of preconditions and effects. Then you have a goal, which is a formula that needs to be achieved in some final state. And the initial state is an assignment over all the variables. Okay. As usual, we are interested in finding a plan, which is a sequence of actions that, when executed, achieve the goal in the final state. Now, a popular approach to solve numeric planning problems is to use our forward state space search algorithm in combination with a heuristic, okay, that is derived from a relaxation of the problem. In this paper, we focus on greedy best first search. So this is a schema where you always expand the node with the lowest heuristic value. And we assume that the heuristic can be cheaply computed and that provides some information to guide the search towards the goal. Now, the triggering observation for this work is that essentially Chen and Thibault observed that a very simple heuristic, which is the Manhattan distance, shows unexpectedly strong performances. So, to give you an idea, we ran the greedy best first search guided by the Manhattan distance over the domains of the last international planning competition versus a state-of-the-art search algorithm guided by a relaxation by a subgoaling heuristic. And you can see here that the Manhattan distance performs much better overall. As you can see, we divided the numeric domains into two subsets. You have the SMP domains. SMP stands for simple numeric planning. These are problems where the effects are constant and additive. While on the right you have we have the linear numeric planning problems, and in this case effects change the variables may change the variable according to a linear expression. Okay, so the questions are, why does such a simple heuristic work so well, and what are the limitations of relaxation-based of standard relaxation-based heuristics? So, as a small spoiler for what comes next, it turns out that the relaxation-based heuristics that work on that work via subgoaling do work very well, but they need to be used properly in the search. And we also need to make these heuristics sensitive to the structure of the problem, so make them sensitive to complex numeric conditions. So this is just some background on the Manhattan distance and the subgoaling-based heuristic. You can have a look at the paper if you're interested in the detail. But from a high-level perspective, these two heuristics are similar in the sense that they both decompose goal conjunctions, so they look at each goal individually. But the difference is that the Manhattan distance computes the estimate from the goal using the numeric error. On the other hand, the subgoaling heuristics take into account the subgoal structure of the problem. And they also consider the cost of the actions required to achieve these subgoals. The relaxation-based heuristic that work on subgoaling can also be used to consider relaxation from a more qualitative point of view, in the sense that they can be used to see what actions do justify the cost of achieving a subgoal, and this is what the HMRP heuristic does. So the trade-off is quite clear in the sense that subgoaling is more expensive to compute but more informed, and it's important to note that this kind of subgoaling heuristic only work for simple numeric planning problems. So, to improve this framework, the subgoaling heuristic framework, we need three key ingredients. So the first one is we need to make these heuristics sensitive to complex numeric conditions. Then we need to lazily evaluate these heuristics. And then we also need to exploit more information from the search, so helpful action and up to jumping action in conjunction with the lazy search. So, for the first ingredient, we revisited linear abstraction for non-simple conditions. So the idea is that, okay, we have heuristics that don't work for linear numeric planning, so we transform linear numeric problems into simple numeric planning problems. And the idea of this transformation is as follows. So let's say that you have this effect, okay? So x changes according to some kind of expression. So if this expression in a state is positive, has a positive value, then this effect is increasing the variable. On the other hand, if the expression is negative, then you are decreasing the value. So what we do is we split this effect into two actions. One for when the expression in a state is greater than 0, so this is a precondition, and this action increases the x variable by 1, and another action for when the expression is negative in a state. So in this way, we obtain a problem that is SMP. And of course, we only use this for the heuristic computation. Now, you can do this abstraction in more sophisticated ways. In fact, this was a technique that was introduced in a previous paper. And but in this work, we revisit this technique and make it parametric. Okay, and we observe that we obtain the best results in our experiment by only using two fixed intervals, so two actions in the abstraction. So as in this example. Okay, so if we, by first adding the linear abstraction, we see some improvement over linear numeric planning problems. So as you can see here, we increase the coverage, but we still don't overcome the Manhattan distance. So for the next ingredient, we have lazy greedy best first search. So lazy greedy best first search is similar to greedy best first search, with the exception that you evaluate the heuristic when you extract a node from the open list. Okay, so when you generate the successors of a state, those successors inherit the heuristic value of the father. And in general, lazy greedy best first search provides a different trade-off between the search effort and heuristic computation time. Okay, so if we add laziness, we get an improvement in coverage, but however, we still don't reach the coverage of the Manhattan distance. So now we need our third and last ingredient, which are helpful actions and up to jumping actions. So helpful actions are actions that are executable in a state and that achieve some sub-goal. So these actions are extracted from the heuristic computation. So usually helpful actions are used to prune all the states that are not reached by helpful actions. In our case, we use helpful actions to discount the heuristic value of a successor state, okay? And we do so in hope that we are focusing the search towards those actions that achieved some sub-goal in the heuristic computation. Then we also have up to jumping actions. So these are helpful actions with an additional an integer that represents a number of repetitions. This essentially means that these actions were extracted by the heuristic, and that in the heuristic they achieved some sub-goal by being repeated m times. So what we do here is we actually try to simulate the execution of this helpful action for m times or less if these actions violate their own preconditions, and we add the resulting state S prime to the open list, discounted by the cost of the action times how many times we had to repeat this action to get the state. And this essentially creates a shortcut in the search. Okay. So this is the full algorithm. In blue, there are the modification to the standard lazy greedy best first search algorithm, and we have that this algorithm is sound and complete. So if there is a solution to your numeric planning problem, this algorithm will eventually find it. So if we put everything together, we actually achieve a coverage. We actually achieve a coverage that outperforms the Manhattan distance, and we essentially set a new state of the art for this type of search configurations. Okay, so what we learned from this study is that if we want to use a relaxation-based heuristic, we need to make the search smarter for them to pay off. And essentially, we also observed that lazy search works very well with helpful actions and up to jumping actions. As future work, we want to explore other search configurations such as multi-queue, portfolio, and also integration with novelty heuristics. That's it. Thank you for your attention. And if there are any questions, let me know.
Thanks a lot, Luigi. We have plenty of time for questions. Anyone? Let me start then. So the thing that I was not sure about is in the very beginning you said essentially that the original heuristic by Thibault and Chen essentially is cheap with respect to the one the original relaxation one, but is less precise, yes. Right? And so do you also observe that one in terms of expanded states, I guess? So the more precise heuristic will expand less states, but it will take more time. Yes. Right. And so it seems to me that, let's say, some of your contributions are in the direction of, let's say, limiting the time, so to say, or let's say, make the heuristic cheaper. Some others instead are to exploit it better. So what would happen if you were using like these kind of approaches with the heuristics of Chen and Thibault?
So you mean like the lazy, so
right.
Everything together? So that's an interesting question. So in terms of linear abstraction, that wouldn't make any difference because that doesn't change how the numeric error is computed. I think that's definitely, it would be interesting to you try that eidolon with lazy greedy best first search, but yeah, well, so those are like lazy greedy best first search trades off like computation time, so trades off like precision for computation time. So and like the Manhattan distance is not expensive to compute. So lazy greedy best first search tries to overcome the fact that you need to compute the heuristic many times for every successor that you generate. So probably that wouldn't make a lot of difference by using that heuristic in a lazy schema.
And you don't have a full action too.
Mm-hmm.
So you cannot.
Yes.
Yeah.
Okay. Other questions? Come on, we have time. So what about quality then, right? So you only showed coverage tables. Do you see, did you measure?
I think we have, okay, so this is the quality over all the domains. So we observe that sometimes it's comparable. In other cases, like plans generated by our schema are longer. That's probably because we are using up to jumping action in the lazy schema. So we are not really trying to minimize the size of the plans or the cost of the plans. So yeah, usually it's longer. It costs more. Yeah.
And do you see any direction in which you can improve in this, or do you think it's inherent to the simplification that you made?
Well, I think we can do something probably by adjusting the way we use up to jumping actions, but that remains for future work. Yeah.
Okay. If someone has a question, we still have a little bit of time. If not, let's thank the speaker again.